Manufacturing is the process of transporting and transforming components and materials to create a final product. Throughout the history of manufacturing, humans have been responsible for the transportation, storage, and control of raw materials, moving them from the docks to warehousing, then to receiving inspection, back to warehouse, and finally to production. On the production floor, these materials are converted into final products and then moved into warehouse again before being transported to their destination or point of sale. This material movement can be viewed as wasted energy due to the multiple handling and transportation stages involved. TPS recognized the inefficiencies in the material handling process and implemented standardization of delivery routes and inventory levels to reduce waste. This adjustment reduced the distance traveled and labor required. However, despite these improvements, the reliance on human labor for material transportation remained unchanged. In the manufacturing sector, the demand for increased customization is driving the need for flexible inventory locations and reconfigurable production sites, creating unstructured environments. Mobile robots offer a solution for these dynamic environments. The integration of mobile robotics in material transportation has eliminated the need for human labor and subsequently reduced factors such as fatigue, turnover, accidents, medical leaves, and errors. Two key technologies that have made this possible are autonomous guided vehicles, AGVs, and autonomous mobile robots, AMRs. The basic components of both technologies include a navigation system that uses sensors to perceive the environment and guide the unit along a predefined path. A control system that receives data from the navigation system and uses it to control the mechanical movement of the unit in conjunction with actuators. A power source, such as a battery set, to provide the energy required for the unit to function. Advanced communication capabilities that enable the unit to interact with other units or systems, such as warehouse management systems. A robust structure to support a specified payload or weight. Closer examination reveals that AGVs compared to AMRs have certain limitations, primarily stemming from their navigation system. AGVs rely on static sensors, such as magnetic tape on the floor or sensors in walls, to guide their movement. While this approach is simpler and more cost-effective, it also poses limitations. In contrast to AGVs, AMRs employ a distinct navigation system utilizing laser scanners to create a digital map of their environment. This allows for variable point A and point B locations, rather than fixed destinations, thus enhancing planning and flexibility. The use of LiDAR in conjunction with cameras also enables AMRs to avoid collisions. Furthermore, AMRs are equipped with advanced software platforms that allow for integration with fleet management systems and communication with standard enterprise resource planning (ERP) and warehouse management systems (WMS) software. The potential applications for AMRs are vast, as they possess a high degree of autonomy. The future of mobile transportation and manufacturing is closely tied to advancements in self-driving car technology. Two key areas of focus for these advancements are energy efficiency and the use of artificial intelligence (AI). To summarize, AGVs can be considered as the early pioneers of mobile transportation technology, while AMRs represent the latest and most advanced iteration of this technology. AGVs rely on static sensors for navigation, while AMRs use cutting-edge sensing technology, such as laser scanners and cameras, in conjunction with powerful communication and AI capabilities to transport materials efficiently. In this sense, AGVs can be seen as the grandpa, while AMRs are the modern Gen Z version of mobile transportation technology.